Okay, I got a signal that I can start. I hope you hear me, so scream if you don't. I'll notice. Hello, I'm Danila. I should have been in this room. Unfortunately, my visa expired, and Swiss immigration didn't like me. So, like, I'm going to present online. So, I gave this talk at CPPCon, and I thought, and I didn't give this talk anywhere else. Unfortunately, CPPCon decided to release my video 2 days ago. So I hope you haven't seen that. This talk will be unique for you. So what I want to talk, so I am a software engineer at Google. I work in the efficiency team. So I'm based in London. And yeah, today I want to talk about STD sort implementation, what it took us to change it, and it's just a good story. All right, so yeah, I said I'm working in the data center efficiency, and what's the agenda for today? We'll talk a little bit of history of sorting, why we decided to change anything, a lot of bugs for sure, which implementation we decided to choose in the end, and what can you do? How can you help? Um, like I guess most of C++ programmers wrote sorting at least once, or at least wrote a call to std sort. But just a reminder, sorting is just ordering of elements. For primitive and usual types, it's pretty obvious. You can write your own comparator if you want. So there are several calls to do that: std sort, stable sort, range sort. We'll talk about everything today. All right. A little bit deeper. Quicksort. What is quicksort? I guess if you had computer science course, quicksort is pretty much in like fourth or fifth lecture for that in the algorithms course, but it's just a reminder. So quicksort, in short, you take any element, you partition by element, everything that's less than this element goes to the left, everything that's more than this element goes to the right. Then you recurse both parts, and surprisingly, you can prove you'll get the sorted range. And this is the code that has been implemented in the first STL by Alexandrov and Lee. It had a quicksort, and quicksort pretty much took any element. It can take an element from first, last, and the middle, and take basically the median of that and partition by this element. So after that, this implementation detail we'll talk a little bit about. They did the recursion up until some threshold, and this threshold was 16, as I remember. And after that, after all quicksort recursion, they decided to do an insertion loop. Insertion sort for all parts that haven't been sorted, and they said that there were some connection issues, but yeah, I had a blip, but now I guess it should be fine. I'm monitoring my connection, so hopefully it's fine now. After that, so you had some sorted range, and after the quicksort, you do the insertion sort for the small parts. It was people believed it was faster. Maybe it is really faster. Some benchmarks prove that. So this was a two-step sorting in the first version of STL. And it looked like that. So you had a random element, and you just partition, do it recursively a lot. And you do it, and you can see some inaccuracies under the elements of size of in the parts of size 16, and then you have one kind of pass over it to sort everything, and in the end you have a sorted range. So this is the implementation that was in the first version STL. This is a fairly good implementation, I would say. Most languages, programming languages, take quicksort as the default, and this has been done in C++, I don't know, 25, 30 years ago as well. Standard library evolved from STL. So STL is standard template library, and now nobody calls it STL. It's actually standard library. And they decided to cement it in the algorithm's header. So you have sorting, which takes two iterators, potentially a custom comparator, which like orders the elements, and some execution policy, but that's not going to be the topic for today. So the complexity must be n-log-n comparisons, actually in the worst case. And this has been changed in C++11. So in C++11, you could have n-log-n comparisons on average. And now it's worst case n-log-n. And quicksort actually might work quadratic time if you take, the biggest element all the time. You just partition one element per recursion level, and you do that linear times, which is not great for complexity and for your CPU cycles. So, all right. Yes. What has been changed? Actually, GCC libstood C++ took the original STL approach and upgraded it a little bit, like when C++11 came out. So they decided to do, like, the loop, the code looks pretty similar actually to what we've seen. It does two calls, some intrasort loop, and final insertion sort. So intrasort loop is almost the same as quicksort loop, but intrasort has this argument on line 8. It is a call to logarithm, the distance, the logarithm of the distance between last and first times 2. What does it mean? What does this argument mean? This argument is actually a limit on number of recursive calls. So if we suspect that we recurse a lot, so we take a lot of maximum elements, or like elements that are close to minimum and maximum, then we just use heap sort. And heap sort is guaranteed to work n-log-n comparisons by making a heap and then extracting a heap one element at a time. So GCC libc.c++ used to logarithm n of base 2, and Microsoft Standard Library does the same. And this is the worst case scenario. It's just a nice animation. I hope it's not very buggy on your screens. It's definitely very smooth on mine, but I don't know what's the connection. So it does a little bit more job than for random elements. So it's okay. It's natural. Sorting performance also is data dependent, and we'll talk about it later. All right. Fun fact, LLVM libc++ didn't do anything for a long time. So in 2014, there was a bug that libc++ standard sort had quadratic worst case algorithm, and it was fixed 7 years later. So the reason why it took so much time is simple laziness, I guess. Nobody decided to fix it for some reason, and there was no pushback from the maintainers of the libc++ LLVM. Just nobody took the courage to fix it all. And after 7 years, me and one of my colleagues decided to finally put an end to this issue. All right. Interesting fact, when we deployed this change, so like libc++ also used quicksort, and when we deployed the change of limiting the recursion, the recursion depth, so we saw that only 0.01% of all calls get into the heap sort fallback. So I believe, like, maybe in computer science courses, like, they tell you, okay, quicksort is good because on real test data it doesn't work bad. And the answer is, yeah, it's most likely is the fact. Google will have, I don't know, millions and billions of calls to std sort daily. So, and that's definitely was a fact for us as well. So maybe that's one of the reasons why it hasn't been fixed for so long. All right. As I said, sorting performance is data dependent, and like it's not necessarily like we don't need like we had a question, okay, how do we benchmark like how sorting algorithms perform? And actually, that's quite reasonable to understand the performance for almost sorted or very interesting patterns that we have, like, I don't know, even odd, reverse, maybe just we have a sorted range and then we have, I don't know, an element which we need to insert in this range. So everything like that. And LLVM actually targeted like this recognized patterns much more than libc.c++, and they got better performance. Actually, at Google, when like we changed, I believe, from libc.c++ to libc++ in 2019, and we saw quite an improvement actually in sorting because of these optimizations. So once and for all, we thought that okay, this is a good estimator of what we can understand about the new algorithm. So we also need to recognize certain patterns in the sorting. And then there's a question: what does constitute a good sort? What is a good sort? And like the answer is, yeah, by standard, it must have analog and comparisons. It should recognize almost sorted patterns, fast for modern hardware. That's actually the hardest part. And fewer comparisons for heavy comparison sorting. So you have like reasonably two types of sorting. Sorting where you sort like, I don't know, integers, primitive types, and like you might want to do a lot of SIMD stuff, and sortings that like use heavy comparators. I know they compare strings, kilobyte strings. So that's definitely, these are two cases, and once is called with bigger ranges, second is called like more often because sorting integers is kind of boring. You need some business logic. All right, so you can see some difference in how libc++ and libc.c++ took some like the performance between two libraries, and this is just an ascending case. And libc++ like finished its sorting long time ago. Probably you didn't even notice, but libc.c++ works like 10 times longer for almost sorted range, and probably you don't want your sorting to do a lot on already sorted range. How libc++ has achieved that? Like the answer is simple. It does on every recursion level. It tries not to recurse, but do some insertion sorts, and it does at most 8 insertion sorts and checks if this 8 insertion sorts. So by insertion sort, I mean it takes an element and tries to put it into the position where it should be. And like it's very easy kind of to track, okay, I have a sorted range up until this point. Let me take an element and put it into the right, so into the right place. And you have like some 8 linear insertions. And if it's sorted afterwards, that's great. You don't need to recurse. If it's not sorted, yeah, probably the pattern is is not recognized. So, and it works well actually for ascending, descending, I don't know, to pipes, and like for well pre-sorted ranges, as we say. Yeah, what happened next is a lot of, I don't know, research has been done in the past maybe 70 years in the sorting space, and there is no such thing as the universal most efficient and fastest sort. And every now and then people come and say, okay, we have a better algorithm. We have, CMD optimized sort. We have, Boost has 4 implementations of sorting, and somebody wrote faster algorithm. Somebody says PTQ sort is the best. So like it's definitely a mess. Like you probably wouldn't even be, you cannot, like, there's also like fear of missing out, like that, okay, there is a new better algorithm for sorting. The question that we had at Google is a bit different. So like we really didn't care which algorithm we use unless it's very performant. What we cared is like that if we see something more performant, we can change to it. And we decided to, okay, let's replace std sort that's libc++ to something else. And yeah, like that was just a good try. Of course, we know that like everything will be broken, but now let's see the full picture, what has been broken. First thing I want to show, it's actually a very simple picture. So I have a SQL script. I just insert into some database 2 pairs of ID1 and ID2, and then I sort it by first argument. And surprisingly, Postgres and MySQL give 2 different results, but the code is the same for both databases. Why is that? The answer is that we ordered by ID1, but not by ID2. And when you do such ordering, the order of the second argument is not guaranteed if the first argument is the same. So, and that's why they have different results. And I mean, surprisingly, there are a lot of such problems, and we call them ties. So you have ties, and how does it constitute, like, I don't know, in C++ code? Well, easily. You have a vector of pairs, you sort by, you have a custom comparator, you sort, I don't know, by the first element or by subset of your struct, and then you kind of have golden test saying, okay, I sorted, like now that's the result. And like when we try to change this to the sort, of course, this assertion might be wrong. And there were quite a lot of such cases. Maybe it's the biggest source of all failures that we had while we're trying to change something, but definitely not the scariest one. So overall, it took us a year to fix everything. So we definitely spent a lot of cycles with like community effort to do that. So it was reaching out to the teams or like fixing our own, and like in complex cases, reaching out to the teams and saying, hey, you have a golden test. How can I make it a little bit less golden? Can we verify properties instead of like having a JSON or protobuf as the result? So definitely it was a fun project. So probably we fixed around 2,000 targets, 2,000 places, like in the code base. All right. So how can we prevent that once and for all? Like, the answer is quite interesting. It's actually coming from randomization. So you just want to randomize the range before sorting, and it's actually enough to claim that nothing. It will break your golden tests like at some point. For example, for 2 elements, you have probability 0.5 that it will be broken. But we decided to put a randomization before sorting, but only in debug mode. And you can, like, how can we implement that in such low-level library? We decided to take the address of a global variable as a seed for if your operating system like macOS supports address space layout randomization, and Linux supports it for as well. So for shared libraries. So and shared libraries support that by default, so it's good. So it was a good seed. And yeah, randomization actually is a good technique to fight such golden tests, to like allow like standard library implementers to change anything. For example, like std sort doesn't promise any ordering of like equal elements, but you decided to write a golden test that depends on it. So overall, randomization actually went a little bit beyond std sort. So we wanted just to implement for std sort, but we found that there are other sorting and like comparison algorithms. So for example, std nth element, which tries to find the element and position it to the place where like if the range was sorted, and partial sort, which sorts just some prefix. And let's look at this picture. That's actually an interesting picture. So std element puts like the element to the place where it would where like it should be sorted in an ideal sorted array. And the order on both parts is undefined. And partial sort does as well, but for the prefix. The trick is actually that std nth element puts the iterator, which you specify as the second argument, to the place, but partial sort sorts up to that iterator. So if you want to if you want the prefix to be sorted up to the 9th element starting from 0, you need to pass +10. So it's actually a quite tricky thing, and we found several bugs for that as well. But yeah, you can see that the difference between this and std sort is that the order, like they have ranges where the order is undefined. And when the order is undefined, well, like it's an ideal place to put shuffle and randomization here. So for nth element, yeah, we decided to okay. So for nth element, we decided to have 3 randomizations. So just before the nth element, up to nth element, after the call to the nth element, and after. So you have randomization for the element that you put in the order and on both parts. That was enough to find quite a few bugs. For partial sort, it's the same, just 2 randomization calls. Okay, let's talk about bugs, probably the most interesting part of all that. Of course, Golden's determinism, like whatever you want to call it, the fix is just to specify some more ordering. If you order by 1 key and you have like golden tests, like ordered by more keys, and that will probably fix your test. That's not the ideal fix, but that works. Sometimes it was a little bit harder. So if you have some sort of data, you might cache it, and then ties are handled randomly. And we saw that like 1 cache had lower hit rate because of our change. That's okay. Like, that's not the best approach. That's probably the hardest thing to fix overall, but we managed to find a resolution for that. You can use stable sort if you don't want sort, and stable sort is an algorithm that promises if 2 elements are equal, they are in the same order as they were in the original array. So you actually don't need any shuffle before a stable sort, because stable sort guarantees determinism. Actually, bugs for standard sort probably were not that bad, but for nth element, we found some logical bugs. Don't look at that const I have here, it's a bug, but yeah, assume you want to compute a median. And median, in some definitions, is like, I don't know, half of the elements on the middle and middle -1 position. And first you call std nth element, you kind of store the result. If the size is even, then you call std element once again, and the result is v of median plus v of median -1 divided by 2, and you just return the result. There is a bug there, and the bug is quite interesting. So if you look at the code, I don't know why my browser decided to interleave some weird things. So you can see that we have first std nth element call and second std nth element call. And after second std nth element call, we access not only position on median -1, but also the position on median. And that's actually not very trivial to it's trivial to miss, but not very trivial to find. And the thing that happened in this code actually is that you call first nth element, you have an element that's put like in the right position, and then you have second nth element, which puts like the second thing on the position. However, the first thing might not be in the place where it was before. You might get lucky because nth element tries to kind of order elements around the nth, but unfortunately, it's not always the case. And you have actually incorrectly computed median. Like, you might think this is a theoretical attack. No, let me show you a lot of bugs. So this is a GitHub repository with 3 key stars. Exactly this happened. So nth element, if it's if the container of even size called nth element and access to elements. However, this nth element actually might override the element that was put to the nth position here. And one more, 3.5 stars, matplot plus plus. So it's like matplotlib, but in C++. They're trying to compute interquartile range, and they call two nth elements on the full range, and then they subtract Q3 index minus Q1 index. And that's not correct, because second nth element might override the results of the first nth element. Another 4.5k stars, the same thing. Another repository, 1.2k stars, two nth elements, just floor of two iterators. And Ableton repository, so some bugs in your audio software. Medical image analysis, that's kind of scary, but that happened. All right, one more bug. So what can you do? You can use this macro for your debug build to randomize unspecified stability. We promise to extend it, to have it more. Hopefully it will be extended to containers, to other algorithms, but for now it's standard sort, nth element, partial sort. Yeah, and that's it. All right. This was the first kind of issues that kind of prevented us from changing one sorting algorithm to another. The second thing is strict weak ordering. Strict weak ordering is a notion of ordering which your ranges must comply with. And if they don't, you might get a sorted array, and it's not very obvious what you want if strict weak ordering is not meant for your custom comparator. And yeah, there are four issues. There are 4 points here: that irreflexivity, that x is not less than x, symmetry, if x is less than y, then y cannot be less than x, transitivity, x is less than y is less than z, then x is less than z, pretty obvious. The fourth one is a little bit more complicated. It's called transitivity over incomparability. So it means that if two elements are equal, then this is transitive. And two elements are equal, it means that both comparisons return false. So 1 is less than 1, no. 1 is less than 1, no. So it means that 1 is equal to 1. You have a custom comparator, all these 4 properties must be met. And unfortunately, like, people write a lot of custom comparators. Like, I mean, who knows what they write? And maybe they have bugs there. Maybe they're not serious bugs, who knows? But in order to check everything here, we need kind of to check all triples. So it's a cubic algorithm. So you're checking all elements and like verify that, okay, x is less than y is less than z, then x is less than z. Okay, so the checks are cubic, but what are the risks if we don't check it? On paper, it's actually undefined behavior. So it's like in the standard, it's written it's undefined behavior, strict weak ordering of your comparator, like, is not met. But like, what happens in practice, like engineering practice? The best thing you can get away with is the range will not be sorted. I mean, okay, it just doesn't sort. Probably you don't know what you want, but okay. Scarier things happen when it fails with segmentation fault, and segmentation fault is pretty real in sorting. And if you write a bad comparator, so on the left you have code which kind of tries to sort elements, positive elements, as like in their ordering, but negative elements should be just before all positive elements, but the order of negative elements is not specified. And on paper, it's a good comparator. Okay, if it's a less than 0, go to the left. If b is less than 0, go to the right. Otherwise, a is less than b. That's fine. And I have here in Godbolt 2 points. So on first Godbolt, I have that number of elements is 30, and on the right I have number of elements is 31. On the left it just does something. Okay, maybe it sorts, that's fine. But on the right it's fails with segmentation fault, and that's actually very bad. It's an issue. We can exploit it. We can do like remote code execution, like scary stuff, C++ in a nutshell. All right. If you really dive into the implementation of libc++ store sorting, then the truth is the following. If number of elements less than is not more than 30, then it will not fail. So all bound checks will be in place, it will be good, it will do something, but it will not crash the program. However, if the number of elements is more than 30, then it can fail with out of bounds. And I honestly haven't written very well tests for 30 plus elements. And we found several comparators at Google, and we had outages, and we had outages, like maybe one outage in like 2 to 3 months because of that. Because someplace the sorting fired because the test had just 5 elements, but in production it like suddenly started to access hundreds of elements. So it's a pretty scary and real issue, and you need to check your comparators for strict weak ordering. How can you do that? First of all, why does out of bounds read even happen? So I told about the quicksort algorithm. You kind of take any element and partition by it, and there is, if you take a median, so it's of 3 elements, you know that there is one element that's less than the median, one element that's like not bigger than, like, say, the median. And you can write one while loop kind of like that while you're trying to partition something. And if your comparator returns a lot of truths, but you know it will return false at some point, it needs to compare, for example, with itself or with the element that's less than you. So you can write. It's actually quite correct to write such thing if strict weak ordering is in place. However, if your comparator returns a lot of truths, that's just out of bounds read. And yes, so one more security issue that we had, we have in standard library. If you have a bad comparator, it's undefined behavior, and it's actually very scary. It's like exploitable in practice. But in order to verify that, we need to check all triples of all elements. It's a cubic algorithm, probably not the best one to implement before n log n algorithm. All right, what we decided to do, I'm not going to dive in many details. Using some maths, we actually can drop the cubic algorithm to be quadratic, but it will only tell if strict weak order is met. The algorithm is the following: kind of sort the range with any algorithm that doesn't fail on a comparator. If it's not sorted, then return false. Like your comparator does not guarantee like any ordering. So, and strict weak order is definitely not there. Then just try to find the prefix of all equal elements. Check that are equal among themselves. So check that these elements are less than all the next, and just remove this prefix. And this is actually enough to, first of all, it's quadratic algorithm. You're kind of trying to find the prefix. You're comparing them with each other and all the rest. So we remove the prefix. It's quadratic algorithm in the worst case. You can find the proof why it's enough, why this algorithm is actually enough to say that, okay, your comparator actually does satisfy strict weak ordering or does not. Still, even if we can drop cubic algorithm to quadratic algorithm, it's still not enough. It's still much more than n log n. If you sort million elements, probably this is never going to finish, or will finish, in several hours for one sorting. And what we found out is that most sortings are small, and in tests, most sortings are small. That's fun. We can use that. And we decided to use this quadratic algorithm for first 100, at most 100 sorted elements. And surprisingly, it went really well. Some caveats, what we need to do. So sorting should not fail. You can write any comparator. Comparator can abort on comparing 2nd and 97th element. And it may never be even called by sorting or by all sortings, production sortings in the world. But you can write any comparator. So, but we haven't found any issues with kind of changing the comparator and then it just check fails on some weird conditions. You can do that, but that was not the case if you're serious about your code. Yes, this algorithm only tells that strict quick ordering is met or not, so it doesn't provide you a triple, and there is no algorithm that provides you like quadratic algorithm that provides you like a triple that violates this condition. Arbitrary comparator can do anything, so it might read from disk, might read from network, so beware. What we needed to do is, first of all, to verify that it doesn't read out of bounds. And so we decided to put the proposal for strict quick ordering in LLVM. It was accepted surprisingly fast. We thought it would take us much more time, but it was good. And first of all, we implemented this out of bounds check. So only in debug mode. Then we included the strict quick ordering checks for sort stable partial sorts. It was released in LLVM 17. You can use it by using this compile options into your projects. libcpp debug strict quick ordering check and libcpp enable debug mode equals 1. So that should be enough, I believe, even now, to kind of give you all runtime failures of your sortings. It took us around 6 to 7 months to fix everything, so like a couple more months for a proposal, but we were fixing while we were like having an RFC. So let's talk about bugs. So which bugs have we found? Most interesting ones. So I'm not gonna I'm gonna show a little bit of bugs from open source, but they were kind of the families of bugs. So first family bug was probably people were thinking that, okay, I can sort anything, for example, a vector, like just with std less, it's just a is less than b. So left-hand side is less than right-hand side. Oh, what I can do is I just can flip the condition if I want to sort in reverse. And like when you're negating the condition, you're having like left-hand side is more than equal than right-hand side. Unfortunately, that's a bug. Comparator of the same element is true, and reflexivity is not met. A little bit more complicated issue of the same sort, but pun intended. But we found this issue is a little bit more than just like more than equal. Is like you have some flag, you want to sort by ascending or descending, and you write, okay, if first is less than second, then return descending, otherwise return not descending. And unfortunately, that's a bug. If descending is false, then comparisons of the same elements are also true, which is not great for your sorting. Another issue, if you have vector of one element, no comparator is called, and that's just, why would you? I would ask, but yeah, because one element is already a sorted element. However, that's still a bug. If you have a couple elements in your vector and one doesn't have any value, that's segmentation fault. This bug, which I showed actually in Godbolt with segmentation fault for 31 elements, it's something like that. So first you check that, I don't know, if you have values of your struct, then you order by this value. But if you don't have value, you want to put them, say, to the front. And yes, and unfortunately, you cannot write the first condition to be true, because otherwise comparator of the same element will be true. So the correct fix for such code is actually to swap for like the two if statements, and that's good code. But better use something like lexicographical ordering. So try to construct a pair of has value and value, or null opt if there is no value, and sort by this pair. But we found a lot of code of like similar patterns. Another thing is a little bit more complicated. Ties are not treated properly, so you are comparing absolute values of elements if they are not equal, but you might forget that some elements have, I don't know, negative values. So two elements might not be equal, but they will be equal. They will get through this if statement, but the return statement will say that they are actually equal. And but you can construct A is equal to diff, B is equal to minus diff, C is equal to diff. So A will be equal to B, B will be equal to C, but A and C might not be equal. They will just not get into this if statement. So beware of properly comparing the ties that you have. We found this bug actually, I can tell, in Google Drive. It was one of the codes that tried to delete garbage collect elements, garbage collect some files depending on their TTL, and they had some issues with, okay, this element should be removed in the future, or this element should be already removed, and they sorted something incorrectly here. Another bug, we had a lot of issues where like lots of logic for sorting, then compare like lots of logic. I don't know, they're comparing like hundreds of fields, and then like you don't even see the sorting call at all in your editor, and then at the end they just push return true. No, that's not correct. Another issue was that you compare two elements and actually you cannot compare them, and comparators might fail. Say, okay, you're reading from disk and you had a disk error. What should you do? Like, that's a good question. Probably you should throw an exception. However, at Google we don't have exceptions, so we found several issues of such sort. The last issue, one of the most, not the last one, but one of the most common ones is comparing floating points. So you're saying, okay, if these two floating points are equal, then I'll compare by saying something else. And if they're not almost equal, then you compare by them. And you might say, oh, it's actually a good practice to compare floating points with some epsilon, just because, yeah, they might have some lower bits different, but they're actually the same. They are not very much different. However, this is a violation of the fourth property. So if A is equal to A plus epsilon, and A plus epsilon is equal to A plus 2 epsilon, it doesn't mean that A is equal to A plus 2 epsilon. You need just to get the epsilon right. And yeah, they might be within the epsilon range, but the first and third elements might not be within the epsilon range. So transitivity or comparability is lost. And yeah, I guess somebody wrote this code even in the audience, because I definitely did when I was just learning C++. So yeah, this is quite common. And remember, every issue that doesn't meet strict ordering can be exploited. So beware. The last issue is kind of a legend in C++ that if your floating vector or floating container has not a number, nones, like you cannot sort, and that's partly true, because when you compare with none, a comparator always returns false, and it means that any value is equal to none. But 1.2 is not equal to 2.2. But comparator might think, yeah, they're equal because you have a none, and that can be actually used if you have a pivot none. Then like it doesn't really matter. Like it's actually quite wrong to partition by none. So this also can be exploited. So the last bug I wanted to show here is if you have a vector of floats and you sort, and you wanted to do reverse sorting, and you maybe forgot the type of the vector or something like that. You just wrote std greater of integers. You thought it was integer, or you changed the type of the vector but forgot to change the std greater template parameter. I included all warnings, -w everything, and there were 0 warnings about every like type mismatch. So that actually happened a couple times. All right, bug in open source. It's Android, so the bug first 2 if statements should be changed. Your reflexivity is not met. Same thing as like x is less than x is not met for like in the library BPF trace, quite popular library. Another thing, so less than equal is used for some reason. Chromium had the forced property incorrect. They, for some reason, compared prefix len, but then didn't compare it at all. I'm not going to dive into that, and I'm not going to dive into that. So about what we decided to change with. So the algorithm that we decided to change with is kind of a mix between block quicksort and PTQ sort, and I'll explain that like now. Block quicksort. So the issue that we had in production, we measured it very carefully, is that when you're like using the quicksort, data-dependent branches are very hard to predict, and processor uses a lot of bandwidth for its branch predictor. And what we decided to do is just store these comparisons in a bit set. And it's very easy for processor kind of to remember the comparison results for, say, 64 elements. And all you need to do is just then traverse this into this bit set. And modern CPU architectures have very good bit traversal instructions. Say, CTC instruction is count trailing zeros. BLSR, it's reset lowest set bit. So like find first 0, get the index, set the 0 to 1, swap the elements that you had. And that actually reduced number of misbranches, branch mispredictions a lot. Another thing that we improved, so as I said, we were taking the pivot. Pivot is like just any element. It was, they decided to, the implementation tried to take the median of first, last, and the middle element. Like the new implementation, which was taken from one of the good implementations, PDQ sort, is just called tucking either. So it tries to pick 3 medians, and then the median out of that median. Well, for some patterns, it just works better. You do fewer comparisons on random. You can prove that, just a little bit less comparisons. So it was a good improvement, kind of to balance the sorting, do maybe, I don't know, a couple less recursion calls for ranges. Yes, so this bit set implementation is actually SIMDable, if I can say that. So it's factorized by the compiler quite well. Benchmarks were kind of good. So for random, it was, I know, from 10 to 50% sometimes. For random strings, where the comparator is kind of heavy, but not the. But yeah, you cannot go SIMD. It was around 10%. And in the end, so I don't want to dive into that a lot. Yeah, in C++ you can write better comparators because of spaceship operator, and you actually return the ordering that you want, like the actual ordering, and you just introduce less bugs, pure bugs. So what we decided, like what happened in the end. So we had this check, we had this randomization. We all called it a comparator sanitizer. We think like it deserves this name. We saw around 7 to 8% performance improvement in production. That's a little bit less than we thought, but okay, we'll take it. We reduced branch mispredictions, was actually very good for CPUs. Fixed, yeah, probably thousands of bugs. Fought the Hiram's law like a lot with this randomization, and most importantly, even simplest things hard to do right. So I decided to change sorting, And I thought, yeah, I would do it in 6 months. Now it took me 2.5 years to finish it. So of course I was not like fully on it. I was just on and off. I was like dedicating like a small portion of my working time, but it was just ongoing. And yeah, lots of new ideas, and hopefully today for you as well. So what can you do? If you use libc++, use these macros to kind of debug in your debug builds to have better sorting sanitizer. And what you also can introduce it in partition, make heap, so they also don't specify any ordering for equal elements or for any elements almost in the case of std partition. And yeah, strict quick ordering checks for nth element will be great because the check that I described doesn't really work because the range is not sorted. So this is not important. So this is the links. So I wrote a lot in my blog, but it's a little bit outdated. So here's the bigger presentation. So this RFC. So this is the sorting change itself with the benchmarks. We'll share the slides with you. And these are my contacts. So I am finished. So I'm ready to take questions. Sorry that I went like a little bit over.
Thank you. Can you hear us?
I can hear you, yes.
Great. I'm passing the microphone to the auditorium.
Okay.
Hi, this won't be a question, but I read your blog post 1 year ago on the topic during lunchtime. And then I got up from the desk and realized, oh my God, what we have done, went back to the desk and fixed the production bug that was hunting us for a month or so, which was due to a poorly implemented operator less and resulted in the condition that you mentioned as tie. And yeah, so this is actually very relevant, and thank you for fixing that bug. I never imagined I can thank it to you, but yeah, thank you.
Thank you. Thank you so much. I hope it's really good. If you work at Google, I don't know, we already enabled it for all Google, but if not, please use this sanitizer.
So, any other questions, Xavier? Yeah, so I think everyone is tired. Maybe the next time. Oh, sorry.
What does this spaceship operator do? You just showed it like for a very short moment. What does it fix?
I would say it doesn't fix like anything on its own. It just tries to hint you that you must use spaceship operators, say, for your elements in the struct. So I believe the change is psychological. It's like what's happening in your head. Now you're not thinking in terms of, okay, this is less than that. You're thinking in terms of ordering. And you probably will introduce fewer bugs with that. So that's the belief. We don't know the statistics yet because we don't have, I know, too much C++20 right now. But we hope that would be a bit better. And I mean, you can write default, I guess, spaceship operators, which also like prevents you from writing your code. So yes, you don't write any code. It's just generated by default, and probably it's correct.
Thank you.
I knew it.
Thank you. Thanks for the talk. A bit tongue-in-cheek, but if you happen to change the sorting algorithm again, are you certain that the test cases you fixed won't be failing anymore?
We hope so, because like randomization and the strict quick ordering check were the two main issues. So we fixed all of them, and we were able to change the sort. And now we're running all tests at Google with these checks continuously. So we don't expect any major issues, or like the work. I guess 99% of work has been done in this area, so I don't anticipate anything else.
Yeah, fantastic. I'm quite suffering from the same problems at my work every now and then, so good job.
Yeah, I think I'm realizing that actually when I was watching at the slide, there's a lot of things that make sense for me because I'm a Googler. So quick question, like by show of hands, does it make sense for everyone when you look at it? Like, I can fix all the tests or I can randomize something. So that's what I was mentioning in my talk. Like we have this insane infrastructure where we've been doing this kind of thing. So we also randomize the flat hash map so that people do not depend on this in their test. And what it allows us to do is you can run this hypothesis and build and run all the tests and realize that you don't break anything. The fact that you can analyze and trace where everything is done is also very amazing. So the fact that you can have this kind of hacker comparison thanks to the language, like the fact that you can have a just defined symbol to enable these kind of things, you don't have this in other languages. So that's exactly what I was mentioning. The power of C++ allows us to do these kind of things at scale.
And Google. So thank you, Daniel. It was really mind-breaking, actually. And yeah, but it's really interesting. Thank you so much for joining. I hope we'll meet you. I don't know where should I watch.
I'll get to Switzerland at some point.
Okay, then please prepare a talk.
Okay, of course.
Or maybe present this one. I think no one
I'll
will
prepare anyone.
Yeah. Okay.
Thank you so much.
See you.